بسم الله الرحمن الرحيم. الحقيقة أهلا بكم أحبتي في درس جديد ودرس متعلق بالدروس السابقة ومكمل للدرس 27. هو الدرس 32 الآن. ليدرس مكونات وتركيبات اختبار الشد، وكذلك تصرف المواد المطيلية والنص المطيلية التي تختبر باختبار الشد المحوري لتسليط القوة محوريا في العينة المستخدمة للشد، العينة المستخدمة للشد مستخدم في اختبار الشد، وكذلك نظر إلى مقومات اختبار الشد ومكونات اختبار الشد ومواصفات المواد المختبرة اختبارا شديا محوريا. And then we've got the most gracious, most merciful, always self-sustained. So today we're in a brand new lecture, mostly associated to the lecture 27. We already been through, we already visualized that actually mostly associated to the very important topics here, in which all the engineers or the entire engineers or civil engineers as well as the materials engineers are looking for, or even the materials engineers are actually trying to visualize or even attempting to comprehend or to have a full knowledge of, or even have full knowledge about. And as you can see right here in front of you, this is a stress, just like we stipulate here. This stress is vertically plotted to the y-axis, or the vertically plotted to the y-axis and the vertical axis, as you can see, as well as the strain is actually horizontally plotted to the x-axis. Here we have two materials, material A and material B is actually pretty much behaving differently or differentiately with each other, or even with respect to each other. Actually, as you can see right here in front of you, this is a point of the elastic limit, or called the point of modeling of the Young modulus. As long as you have a point of modulus, or even as long as you have a point here for Young modulus of the modulus of elasticity, or even the elasticity moduli, or even the Young moduli, as you can see, this point at the curve for the both material A and material B can be mapped exactly to the stress vertical axis at which or the vertical axis of y at which the stress is actually uploaded right at, as well as you can map this point right into, you can map this point right into the horizontal axis of this strain plotting, or even at which the strain is plotted right at, and you can extract both the stress, the nominal stress, as well as the engineering stress value from the vertical axis, or the vertical plotted to the vertical axis, as well as the strain value. We can extract the strain value plotted horizontally to the x-axis, as you can see right here in front of you. So both materials are behaving differentiately with respect to each other, just because the material A is pretty much differs from the material B, pretty much different, or even differs from the material B as represented, or even as visualized in the following graphical representation. Bismillah ar-Rahman ar-Rahim. As you can see right in front of you, the materials are actually, besides the material are actually behaving differentially with each other, or even with respect to each other, they're actually behaving differently just because the contents of the alloys at which the specimen of the materials, or even the material specimen, are used, or even tensilely tested, as you can see right here in front of you. The stress, just like we stipulated, the stress is actually, as you can see right in front of you, this is the strain A, and the strain for E for the alloy B, or even the strain for the spaceman actually used for the A materials, or as well as the strain here actually indicated as we stipulate, or even as is plotted right before you, as you can see, for the point B of the material B itself, or the material B himself, as you can see right in front of you. So the material here is actually indicated by the curve line. Material A is actually indicated by the curve line, as well as the material B is actually indicated by the curve line of material B, as well as both points of the upper point, or even both points for the elastic moduli limits, as you can see right here before you, is actually pretty much visualized by the curve behavior, or by the curve manner in a graphical representation of the stress strain curve for both for dimaterial behavior, or even bilateral behavior. This behavior is actually called bilateral behavior. Bilateral behavior يعني التصرف ثنائي الجوانب أو ثنائي الجانب. هنا تصرف لمادتين. There's actually a behavior, or even acting for two materials that actually different in contents, or even different in formology, as well as different in the type, or even the sort that actually they are going with. As you can see, this is the vertical is actually pretty much plotted to the vertical axis, or even the stress is pretty much actually vertically plotted, as well as the strain is actually x horizontally plotted, as you can see. And as we indicate that the stress is actually a blocking perfect signal indicating the type of stress, or indicating that the stress is actually stress, or even the plotting component of the stress strain diagram is actually stress, as well as many words, or even words or initials, or even letters will be placed right by, or even the stress prefix will be conjugated with letters to indicate that the stress type is actually of certain use, or even the stress is actually of certain sort, just to indicate that the stress is of certain sorts here. يعني الكلمة سيجما تكون مقترنة مع حرف أو كلمة the word sigma or even the prefix سيجما أو البادئة سيجما، البادئة اللاتينية سيجما أو البادئة اللاتينية أبسلون، أو بالنسبة للإنجينيرنج سترين أو بالنسبة للانفعال الاسمي أو الانفعال الهندسي سوف تكون مقترنة بحرف أو بكلمة للدلالة على أنه أنه الاجهاد أو الانفعال يكونان من نوع معين. So this is an epsilon, or even for the engineering stress or the nominal strain, is actually pretty much conjugated with words or even a term, with word or even a letter or even a term that actually just to indicate that the stress is used or even the stress extracted or obtained is of certain sort, or is of certain type. The figure 7.2 is the way to measure stiffness with the elastic moduli, or the way to measure stiffness, or even the way to gauge this stiffness with the elastic modulus. And the elastic modulus is measured, or even the arc modulus is actually measured or even gauged. Consequently, the stiffness of the metal by calculating the slope for the straight line, or even for the line and the stress strain graphical representation curve to the proportional limit as illustrated in figure 8.2a. And for the materials that actually does not satisfy line with the graphical representation curve of the stress strains, so the elastic moduli will be measured. Consequently, will be measured or will be gauged. Then afterwards, this stiffness by using the initial tangent modulus or the initial tangent criteria. The initial tangent criteria is said to be the slope for the tangent of the graphical representation or the graphical stress strain curve at the point of origination, which means the commencement of the curve as illustrated or even as clarified in the figure 8.2b. As you can see right here for you, this is 8.2a and 8.2b. As you can see right here, this is stress actually vertical potential we stipulated before, as well as the strain is actually horizontally plotted to the x-axis, and the stress, just like we stipulated, or just like we stated that the stress, or formally, just like we formally stated or previously stated, or just like we predecessorily stated, that the stress is actually pretty much plotted to the vertical axis. Here we have the initial, as you can see here, for the A, or even for the A scheme, or even for the A diagram, the stress and strain are pretty much perpendicular or even pretty much orthogonal to each other, intersected at the point of origin, which is point O, at which the point is the curve is at which the point, or even the point at which the curve is actually launching or even released from, by increasing the stress amount or even by increasing the stress rate, or even phased by an increase, by a corresponding increase or even by a corresponding increment or escalation in this strain rate in the same instant, to the same, or at the same instant, or in the same instant. As you can see here, we're just going to have to take the modulus of elasticity triangle. This triangle is actually indicating the region of elasticity, or even indicating the region of modulus of elasticity. So this is the theta, this is the angle, is actually pretty much trapped or even made by the hypotenuse with the horizontal axis of E, representing the E plot, or representing the E values, which is pretty much indicating the engineering or even the nominal strain, as well as the adjacent, as well as the opposite here will be the sigma, or the value of stress. So we have the theta here, the theta, as you can see right from here. The theta is tan theta. The theta is measured here by right between the stress and strain at the same time. Strain is the adjacent for the theta, and the stress is the opposite for the theta. As you can see, this from this point right and up at this point, or from this point right and up at this point exactly, particularly this line or this oblique line is actually called the hypotenuse. The hypotenuse, يعني الوتر. As you can see, the E modulus here, or the Young modulus, or the modulus of elasticity, or the elasticity moduli, or even the Young moduli, whatever you could call it, and any form that you actually you would choose to call the E right with. As you can see, you would choose any form. You can just choose any form. You can choose any form just to call the E with. The E, the Young modulus, or even the elastic moduli will be computed by using the tan theta, or even by using the trigonometric representation or the trigonometric expression of the stress and strain to measure the E, or even to gauge the E empirically to measure the E, which is the Young modulus of the modulus of, or the modulus of elasticity here, equals to, will be equal in this case, will be equal to tan theta equal to stress strain. As you can see, the theta will be equaling to arctan stress strain. the arctan stress strain. So the theta will be equal to arctan stress strain, the theta expressing the Young modulus, or expressing the modulus of elasticity. In this curved line, or even as you can see right in front of you here, the curvature will occur in this shape, or even will occur in this scheme or diagram, as you can see right in front of you, expressing the point of elasticity as well as expressing the point of ultimate tensile stress, denoted by the UTS abbreviation, or denoted by the UTS initials. So the tangent line here is the proof stress line, is actually intersecting with the point C to express the proof stress, at which the stress, to guarantee the material that would not be failed at certain limits. In this point, the material will not be failed at this limit. Exactly at this point lies, or even at this point, is actually plotted right to the curve. When we map this point, what's the vertical axis? When you're going to extract the value of the proof stress, which is pretty much indicating the value of 0.01% of the strain rate, or of the strain percentage expressed by the vertical, or expressed by the horizontal axis plotting, as you know, or by the horizontal axis plotting or plot. And as you can see right in front of you, this is the initial tangent. This is the initial tangent slope, as well as this is the slope here for the tangent slope. This is the initial tangent slope, and this is the tangent slope. And the B here is at the point B exactly, indicating the stress and the elastic limit, or the stress of the elastic limit. The B is actually expressing the point at which the elastic limit is pretty much valid, or even pretty much applicable. After the point P, the plastic elastic region will begin, or even will be triggered in the same time, or in the same instant, just like we indicated before, or just like we visualized before, just like we used to learn that the elastic limit will be measured by using trigonometric ratios, such as we have theta here mapped, or even have a theta here made by the hypotenuse, as well as right between the hypotenuse and the horizontal axis of E plotting, or the horizontal axis of the E ratio or percentage, facing the stress valued plotted to the vertical axis of the opposite for the angle theta. So the opposite of the angle theta, just like we said here, just like we stipulate that the stress is the opposite of angle theta, and this strain E is the adjacent for the angle theta, and this point, or the oblique line, is actually called the hypotenuse. The hypotenuse الوتر، يعني الوتر، والthe opposite هو المقابل اللي هو الستريس اللي هو مبين فيه الإجهاد أو مبين عليه الإجهاد، وكذلك السترين هو المجاور للوتر أو المجاور للزاوية المحصورة بين الوتر، or is actually pretty much adjacent to the excluded, or even better for us to say that pretty much adjacent to the restricted theta. Or the theta bounded between the hypotenuse and the adjacent. As you can see, where the adjacent is actually presenting, or even the adjacent is visualizing the strain plot, or even strain rate or percentage, and as well as the opposites actually represent the vertical visualization of the stress plotting in the same time. So the strain and stress is actually pretty much perpendicular and orthogonal to each other, and intersect the same point of origin. It's called the point of originations, at which the curve of stress strain representation is actually launching from. Bismillah ar-Rahman ar-Rahim. حقيقة, as you can see right here in front of you, this the Young modulus is equal to tan theta equal to stress strain. Just by looking at the theta, or by calculating theta, you're just gonna have to calculate, or by calculating theta by the desire, or even by the requirement to extract the theta, or to obtain the theta. All you have to do is just set the theta for the arctan of the stress and strain, and you're going to find the theta which is considered, or even which is mainly considered the Young modulus, or even the elastic model extracted for this certain type of the curved stress strain representation. And as you can see right in front of you, this is the linear stress strain diagram representation curve, representing curve, as well as the curved stress strain diagram in the form of curvature, or in the form of curved line. This is made called the figure 8.2 determination of Young modulus for the materials that have a stress strain diagram in the form of straight line, and the materials that has stress strain curvature, curved origin stress strain curved line. Stress strain curved line diagram. In case of the Young modulus, differs according to materials used. So each material has its own Young modulus, or has its own elastic moduli to go with, or even to deal with, as illustrated, or even as it is clarified in figure 9.2. Bismillah ar-Rahman ar-Rahim. Now, as you can see right in front of you, is actually the geometrical strength is actually determined or even scaled by the ton to centimeter squares or ton centimeter squares. This is engineering stress, or the nominal stress is plotted vertically to the y-axis, as you can see right here in front of you, and this indicates the many of or indicates the structural curve representation diagram for many of materials or many of alloys or metals, actually pretty much illustrated in this diagram or in this scheme, as you can see right here before you. The alloys or even the metals or components actually illustrate, or even the metals components comprised by the entire stress strain diagram representation is as follows: the carbon or plain carbon steel, or the carbon silicon steel or structural silicon steel, and aluminium alloy, as well as copper. Copper is the metal. Aluminium alloy is actually pretty much considered as the aluminium alloy, considered an alloy of aluminium, or even aluminium volume. فوليوم or alloy. يعني السبيكة هي بالإنجليزي volume or alloy. يعني volume أو alloy. As you can see for this, aluminium alloy has the curve extending from the point of origin at which the point the or even the point at which the engineering stress or the nominal stress as well as the nominal strain are intersected right at. As you can see right here for you, this is the copper, chemically sampled as Cu, and the aluminium alloy is actually chemically sampled as Al, or Al positive, or even Al digitalized, and certain digits, or even certain encrypted in certain digits that indicate that the aluminium alloy, or indicates the digits are indicating that the aluminium alloy or the aluminium volume they're actually dealing with is pretty much of the same sort, or even pretty much of certain sort, or and particular sort, as you can see right in front of you. Aluminium alloy is acting as a ductile material, as well as the copper is acting as a ductile material, as well as the monoil metal and the soft steel and the malleable iron or even wrought iron. As you can see, soft steel and mild steel and the wrought iron or even malleable iron, يعني حديد مطوع, and magnesium alloy or even magnesium as metal here, as well as the cast iron, as well as the zinc. As you can see, the engineering strain or the nominal strain is actually pretty much plotted to the horizontal axis in a form, or even measured by the centimeter. This is the geometrical strain or the nominal strain, and the engineering stress is actually called the nominal stress. The nominal stress uploaded to the vertical axis, or even plotted vertically, measured or even scaled by the ton centimeter squared, plotted with the digits, or even with the amounts of 1, 2, 3, 4, as well as the engineering strain is plotted actually horizontally with the amount of 0.00 and 0.008. As you can see, this zinc here is actually pretty much used to be with a high elastic moduli, as well as the cast iron is even higher elastic moduli, or even the magnesium is higher more aesthetically you can go in the stress strain plotting diagram or representation diagram, more elastic moduli you will get, or even more elastic moduli you can get, as you can see right in front of you. But the elastic moduli for the, let's just say, for the structural steel carbon or the structural steel alloy, as you can see right in front of you, the elastic moduli is actually pretty much higher than, or even the zinc has elastic moduli pretty much higher than the structural. The cast iron, as you can see right here for you, is pretty much has an elastic moduli, or even a Young modulus is pretty much higher than the structural, or even higher than the aluminum alloy. Let's just say for saying, all right. So the cast iron will be considered as more ductile than the aluminum alloy, as you can see right here for you, or even the cast iron will be considered as more brittle other than the aluminum alloy. The aluminum alloy is considered actually pretty much of a high elastic moduli, so consequently, or as a result for this, or even resulting in the ductility, or even resulting in the ductility particularity to be gained by the aluminum alloy, as you can see right here for you. This diagram is actually illustrating a certain behaviors, or even a multiple times, or multiple lateral behaviors, or even multiple aspect behaviors for plenty of components or alloys, or even plenty of elements represented in the stress strain curve graphical representations between the engineering strain as well as the engineering stress, pretty much intersected or even orthogonal and perpendicular to each other, intersect at the point called the point of origination, at which all or the entire stress strain curves indicating the differentiated behaviors for the entire components represented in the curves are launching right from. The figure 9.2, the curves of strain strain for a variety of materials, or even for variety of alloys, illustrating the different Young modulus, or even illustrating the differentiation of Young modulus according to the materials used, or according to the specimens or alloys used. The elastic limit. 2. is maximum stress the metal can withstand with the sustainability of a plastic strain, or even the plastic strain after the affected load, which means there's actually permanent. It's going to be like a permanent formation after the affected load, which is represented by the point B and denoted by sigma E. Sigma is prefix as well as is conjugated with an E letter here to be considered as indication, or even to be considered as an index for a certain type or even for a certain sort of stress obtained or even extracted. E 3 اجهاد الخضوع yield stress. 3 is yield stress. Is a stress occurs at which a noticeable increment of elongation will occurs right at, or even stress with a noticeable elongation rate without any with any increase of loading, which means the strain increasing with correspondingly with the stress, as you can see right for this. In this point, the conversion from the elastic strain right into the plastic strain will be done, or even will be achieved, which we can say, or we can tell about the case here. It is the end, or even about the case is the case of elasticity and the beginning of plasticity in the same time. Four, the metal, in fact, has a yield stress, but not a point. Is a region, but not represented by OP, but not plotted by a point. Is actually plotted entirely by a region, represented or even clarified in the figure by point C and denoted by stress yield, or even denoted by sigma Y. You know all about the sigma, as well as you know all about Y, as well as it is conjugated with the sigma to indicate a certain sort of stress, or even a certain type of stress extracted or even obtained at a certain point of the stress strain curve track, or even stress strain curve course. The proof stress, اجهاد الضمان. Metals are characterized with elasticity, but the consequence or the outcome of the metal testing is actually clarifies that the metals don't have any yield region, or even do have a yield region regarding just because due to the plasticity particularity. So a certain stress should be gained to express the strength of material, or to express the strength of metals, as well as the resistance of metals in case or in the elastic region. And this stress is actually called the proof stress. So the proof stress is actually a very much expressive stress here for the behavior of metals, or even for the to indicate, or even for the indication of metal strength in the elastic region, or the metal strength, or even the metal resistance for any loads exerted at exactly the elastic region, right in the elastic region. And the stress or proof stress can be identified that stress occurs in the testing specimens while loading in a very much a proportional elongation equal to a percentage or specific percentage of the gauged length. And mostly the proportional elongation will be used to assign a proof stress is between, or even is ranging between 0.1% and 0.5% of the gauged length. Most of the computations, as well as most of the empirical calculations, the certain amount of stress will be taken in the amount, or even in the value of 0.2%, and the proof stress value is as follows. يعني قيمة إجهاد الضمان هي كالتالي. The proof stress is equal to proof load to the proof load with the original cross-sectional area. Proof load with the original cross-sectional area. Stress proof is actually proved here as the conjugate with the word proof is actually to indicate that the stress is actually extracted here is a proof stress, or a proof, or it is stress indicating the stress material, the strength of material within the elastic limit only, equals to F proof, which is the maximum, or even the proof load and the area. And to determine the proof stress graphically, we should determine the proportional elongation given to the plot, or plotted even to the horizontal axis of x, representing the strain. Then plotting a straight line parallel to the proportionality line. This straight line intersects pretty much with the stress strain graphical representation curve in a certain point. So the corresponding stress of the point will be the proof stress mapped to the vertical axis of y, at which the stress is actually plotted right at a required, which is pretty much required proof stress, resulting in the obtaination, or resulting in the extraction of the required proof stress, as illustrated, or as clarified, or as disambiguated, or as visualized in the figure 10.2 and denoted by the stress proved, or sigma proof. And as you can see right here, this is the shape that actually pretty much As you can see right in front of you, the stress is actually denoted by the sigma, by the prefix or Latin prefix sigma is actually plotted vertically, as well as the strain is denoted by the epsilon or the E, denoting or indicating the engineering strain, or the nominal strain is actually plotted percentage-ally to the horizontal axis of X. As you can see, whatever the pros of the roof stress will be taken in the value, or even ranging between 0 and 0.2%, as you can see, will be drawn right, particularly from this point to the horizontal axis, right into the point at which it will intersect with the stress strain curve representation, and the point will be considered as the point of proof stress, will be exactly mapped, يعني تسقط mapped يعني تسقط. The point is actually at the stress strain curve, extracted from the alignment, or extracted from the intersection between the proof load, or even between the proof stress slope, or between the proof stress slope, right at exactly at the stress strain curve, and will be mapped to the vertical axis at which the stress is plotted to extract the value of the proof stress, sigma proof, or indicated as sigma proof, as you can see right here in front of you. And this is the strain is actually percentage-ally plotted to the horizontal axis of X, as well as the stress is actually linearly plotted to the vertical axis of Y, as you can see right here in front of you, denoted by the sigma, and the which is representing pretty much the representing the indication for the engineering stress or the nominal stress, and the strain is indicating the representation or the visualization of the engineering strain or the nominal strain in the same instant. The figure 10.2 is a graphical representation curve, illustrates the method to determine or even to specify the proved stress. Article 2.8.2, the mechanical properties of metals in the elastic region. يعني الخواص الميكانيكية, the mechanical features of metals in the elastic region. The plasticity, or even the plasticity, or in the plastic region. The plasticity is the ability of materials to have to possess or even to retain a permanent formations, which means that the material is no more or no longer recoverable for its original size and shapes after the affected load, or even which means the material is no longer be able, which means that the material is no longer or will no longer be able to retain or even to recover the original sizes and shapes or the original dimensions after the affected load. 1. As you can see right there, the Article 1 for the, or the Category 1, or Article 1 for the category, as you can see right there, the Article 1 is actually indicating the UTS, the ultimate tensile strength, or the tensile strength, ultimate tensile stress. The ultimate tensile stress or the ultimate tensile strength is the value or even the scaled value for ultimate load at which the material can withstand or the material can tolerate, and equals to the maximum load susceptible or even maximum load experienced by the tensile test spaceman divided or even to or with the cross-sectional area, the original cross-sectional area of the spaceman used, which is represented in the figure by the point D, or even which is pretty much visualized or even clarified in the figure by the point D and denoted by sigma UTS, or even termed by sigma UTS, ultimate tensile strength. This is the as you can see right in front of you, this is the prefix or even the denotation. The UTS is the denotation conjugated with the sigma prefix, Latin prefix, to indicate that the stress we're actually reviewing right now is of certain sort, which is pretty much required to be denoted as the ultimate tensile stress or even the ultimate tensile strength. The equation 90.2 visualizes the relevance or the arithmetical relationship or the arithmetical relevancy to the sigma UTS or the sigma ultimate tensile stress or the ultimate tensile stress in the material used, or ultimate tensile stress to indicate the ultimate tensile stress or the ultimate load to be exerted axially or even to be applied or to be imposed axially to the testing spaceman or the testing spaceman, as we indicated before or as we stipulate, equals to the Fmax or the maximum load at which the material can tolerate with the cross-section or with the original cross-sectional area of the spaceman used to conduct the test for. The value of our ultimate tensile stress, the ultimate tensile stress value is actually offers a measurement or it offers a scale for the ultimate tolerance or the ultimate tensile strength of the metals, which allows or even which permits to compare the metals and the material selection for engineering architecture or for the geometrical architecture. Commencing point T, the necking will start to be formed or even will be initiated till the specimen will reach a state of fracture or even till the specimen reach the phase of fracture, and the variations entirely all along will be denoted as necking, or the entire variations all along will be denoted as neck variations. 2. Fracture strength. Fracture strength is the stress at which the fracture of the spaceman will take place, splitting the spaceman into two halves, represented by point E in the figure, or denoted, or even visualized by the point E in the figure, denoted by the sigma F. F is the word indicating the fracture, and conjugated with the stress, a Latin prefix of stress, indicating the stress, that the stress is actually of the certain form. 3. A ductility is able to material to form or to be formed, and the ductility of the metals is actually measured, affected by the tensile load, by calculating the percentage, or even by calculating the elongation ratio, EI, as follows: EI equals to delta L pi times, or even by 100 equal to LFL naught times 100 equal to maximum strain at which the material can go with, or at which the material can get along with, times 100. This is the equation 20.2 of the course. This is actually pretty much the equation 20.2 in the course, or if of the course, where L naught is the original gauge length of the spaceman, and LF is the gauge length of the spaceman after the fracture, or even post to the fracture spaceman gauge length. The ductility is also measured by the percentage of escalation of the transversal cross-sectional area, RA in percentage, or RA percentageized, as follows: RA equal to delta A times 100 equal to AF, as you can see right here, right here in front of you, or even right here before you, times 100. This is the equation 21.2 of the course. Well, A naught is the original cross-sectional area of the spaceman, and AF is the instantaneous, or even the after fracture, or even post-fracture spaceman cross-sectional area. Post-fracture يعني بعد الكسر. Post-fracture spaceman cross-sectional area. So now the ductility value for the elongation, or even with respect to the elongation, is pretty much different than the ductility value extracted with respect to the area oscillation, or with respect to the area variation. With respect to the area variation. Article 3.8.2, the measurement of the permanent notch. Whereas about the knowing, or even by the computation of the permanent notch magnitude, or the final elongation after the effective load from the stress strain graphical representation curve, there are actually major three cases according to the effective load value. You can also regard the figure 6.2, as you can see, illustrated right at. The illustration will be right at the case 1. The load is in an elastic region, illustrated figure 11.2a. There's actually pretty much a permanent notch, and the spaceman is actually the spaceman will be able to recover the original size and shapes after the effective load, or even the spaceman will be able to recover the original dimensions. The case 2, the load is in a plastic elastic region, illustrated in figure 11.2b. The permanent notch is actually the intersection between the parallel line of the proportionality line to the proportionality line in the curve and the elongation axis. So the case 2, the load is in the plastic elastic region. The plastic elastic region, or the interstitial region between the plastic region as well as the elastic region, illustrated in figure 11.2b. The permanent notch is the intersection between the parallel line to the directional proportionality line to the proportionality limit in the curve, as well as the elongation axis, or the extension axis. The case 3. The load is in the plastic region, illustrated in figure 11.2g. The permanent notch is the intersection of the straight line parallel to the load axis as well as the extension axis. As you can see, the A. This is the this is the figure 11.2a illustration indicates that the load and extension, or even load and the elongation, pretty much illustrates in the vertical, or the load is pretty much illustrates as an intersected line in the point of originations at which the stress strain curve, or the stress strain graphical representation curve, will be generated right from and lodged right upward, or even will be escalated right upward in any linear increasing of stress, or even linear increase of load, resulting in linear increasing of stress in a corresponding extension, or even corresponding linear certain value of strain to a value called the elastic moduli point, at which the stress as a strain is no longer be linear right even after, or even pretty much longer be linear, or even right linear even after the point, or even after. as you can see right here for you, the load is applied to the material, and the stress strain curve will be able, or even will be generated right from the origination at which the stress strain curves, or the stress strain axis perpendicular, both perpendicular or orthogonal axes are intersecting right at. Here comes the elastic region, or even here comes the elastic indication for the stress strain curve upward oscillated till reach a certain limit, occur the upper yield point, and then the nicking will actually take place to reaching the ultimate tensile stress, and then the fracture strength will be even considered as the conclusion for the track of the stress, or even as the conclusion for the curve, as you can see, or not the conclusion for the curve, but for stays be like as the a point at which the material will be split into two halves. Will be splitted into two halves. The elongation here is actually, the permanent notch is actually indicated by the proof load inclined slope, or even the proof load's inclined line, as you can see right from pretty much parallel to the elastic line, or even pretty much parallel to the elastic axis, which is generated from the point of origination at which the both load and extension curve, or load and extension axis are pretty much intersected right at, called the point of origination, just because the elastic line, or the elastic axis, is actually pretty much generated right from the upward to the upper, exactly to the upper yield point, and then the nicking in the same case, and then the ultimate tensile stress and the fracture strength, or even the fracture point for the displacement, at which displacement, just like we said, right, or just like we said before, the displacement will be split into two halves as a result for the fracture, or as a result for load distribution, or even as a result for the load load distribution to the shoulders. As you can see right here for you, the permanent notch is actually indicated right between, or even trapped, or even exclusively restricted right between the point of origination to a certain point in the horizontal axis of X, indicating the extension, or certain point of extension plotted to the horizontal axis, just like we stipulated, just like I want to remind you, and the visualization we already done, or we've already been through. And the gene is the same as this. The permanent notch here for the elongation in case if you're having a plastic region. So the permanent notch for the plastic region will be from the point of origination to a wide spread point, or even to a broader point to the extension horizontal axis, to a wider point of plotting, or to a wide or broader point of plotted to the horizontal axis of extension, as you can see, whatever, which is mainly, or by the way, can be mentioned, or even can be considered as the x-axis. And the load is actually linearly increased by the increase, or the linearly increased, or even linearly augmented and oscillated linearly with the strain to a certain limit called the point of elasticity. After the limit of point of elasticity, I just want to visualize this. We just want to visualize this. After the point of elasticity, here comes the point of upper yield point and the lower point, as you get point, as then the nicking will take place till reaching an ultimate tensile stress of UTS point plotted to the or even plotted to the stress strain curve behavior of the stress strain curve track to reaching by the action of stress, or even action of the load imposed axially to the displacement to the point of a fracture, to finalize the action of, or even to finalize the effect of the load axially imposed, or even axially exerted, or even axially applied to the displacement. So the figure 11.2 is illustrating the measurement, or even illustrating the scale of the permanent notch in case of the of having an effective load in the elastic region and the plastic elastic region, or even in the plastic region only. Article 9.2, the stored energy. Article 1.9.2, the resilience, الرجوعية, is the energy that metal can store at loading, then bring it back again, or even then reload it back again after the loading in the only in the elastic region. Also called the elastic, also be noted, or also it can be noted as the elastic energy, which equals the work done then by loading to inflict, or even to make an elongation to the elastic limit value to the proportional limit in the consideration, which means the bigger energy, or the biggest energy, or even the hugest energy in the elastic limit. The value of resilience is determined by the following equation. The variable resilience is 1 to 2 by the proportional limit corresponding load times the proportional limit corresponding, or the proportionality limit corresponding extension. The proportionality corresponding load times, or even by the proportionality limit the proportionality limit corresponding extension or even elongation. ER equals to 1 to 2 times FP times delta LP. Delta L is the extension resulting from the strain distribution as a result for stress imposed, or even as a result for stress application, times the FP is the load corresponding, or even load versus the load corresponding to the proportionality limit in the stress strain graphical representation diagram, times the ratio 1 to 2, as you can see right here for you. Then it equals the work done by loading to inflate elongation to the elastic limit, which pretty much value to the proportionality limit in consideration, which takes the value of the proportionality limit in consideration, which is the biggest energy, better for us to say, the biggest energy in the elastic region, or in the elastic frontiers. The value of resilience is determined by the following equation. The resilience is 1 to 2, the corresponding limit to the proportionality, or the corresponding load to the proportionality limit, times, or even by, the corresponding extension or elongation to the proportionality limit. This is the equation 42.2 of the course. The resilience is the area of the triangle below, or even area of the triangle of this straight line curve, graphically represented for the load and extension, or for the load and elongation. The coefficient of resilience, or even the moduli, or even the modulus of resilience, you are equals the resilience to the size or the volume of the testing spaceman, which means the resilience, or even which means the resilience for each unit volume, and equals as follows, or equals the following. You are equals to 1 to 2 times FP. FP is an indication of force or even load applied in the proportionality, or the load applied corresponding to the proportionality limit, times delta LP, or even the extension at the proportionality limit, equals to 1 to 2 times FP, the load at the proportionality limit, or even the load of the proportionality limit, or even the load or the force applied axially corresponding to the proportionality limit, times the extension or the elongation corresponding to the proportionality limit in the same instance, equals to 1 to 2 times stress P, or the stress at exactly the proportionality limit, or the strain times by the strain E, indicated by the E English letter conjugated with the P, indicating the proportionality limit existence, or the indicating the that the strain sort that we're actually dealing with here is actually pretty much conjugated, or even pretty much lies in the elastic, or pretty much corresponding to the proportional limit, resulting in the following overall simplificative formula of the equation, or the simplificated form of the function, as you can see right here in front of you. For the modulus of resilience, you are equal to 1/2 times stress P times EP. Stress P is the stress at the proportionality limit, or in the proportionality limit, times the EP is the strain in the proportionality limit. This is exactly, or this is absolutely, the 23.2 equation of the course to be considered. Which means EG, yani A, which means the modulus of resilience equal to 1/2 stress by strain, or the stress times stress, and according to the illustration of figure 12.2 is the area of triangle below straight line, or even the area of triangle of the straight line, straight line of the stress strain graphical representation line curve, or even graphical representation curve at the in the proportionality limit, or corresponding pretty much to the proportionality limit. This, as you can see right in front of you, this is the proof stress. This proof stress is actually determined from the limitation between, or even between the range, or ranging between the 0 point of origination at which the both axes of stress strain intersected right at, which is pretty much which are very much perpendicular and in the same time orthogonal to each other, to a certain point of the extension, or a certain point of the strain plotted to the horizontal x-axis for the visualization of strain is in the range, or even the amounted, or even valued as 0.02, as you can see right here in front of you. This is the strain, and this is the stress. This is the oblique line, or this is the inclined line, and which intersects with the stress strain curve at a certain limit, or even exactly at the point of elasticity index, and will be mapped to the vertical axis of the at which the stress is plotted, to extract the proof stress value from the mapping, or even from the corresponding stress strain curve point, at which this point of stress strain curve, a certain point in the stress strain curve indicates the proof load, or even indicates that the oblique line is actually launching, or even generated from the point. 0.2% is actually intersect with the stress strain curve at a certain point, lies at the same curve, or lies in the same curve. The figure 12.2 is the graphical representation determines or even illustrates or clarifies or disambiguates or even visualizes a way or the method to determine or to specify the modulus of resilience. As we have seen in the relevancy 17.2, the E equals to stress P, stress is strain E, or the strain B then, hence yield, or in yields, the strain B equals to stress PE, as you can see around it. The E is the elastic modulus as well as the stress. P is conjugated with P letter, indicating the proportionality limit, means or even indicates that the stress is actually measured or even scaled is of a certain sort, which is, by the way, the stress in the proportionality limit. And by evaluating in the equation 23.2 of the course, we get the value of the modulus of resilience in terms of the modulus of elasticity E, or the elastic moduli E, or the Young modulus E, and the proportionality limit C, stress P, or the proportionality limit stress P, indicated as sigma P. As you can see right in front of you, the finalized equation, or the finalized function, as you can see right in front of you, will be written in the form of UR is the elastic moduli, or the modulus of resilience, equal to 1½ times stress P equals to 1½ times stress P squared, which is pretty much just like we stipulated, just like we indicated that the stress of certain sort, which is, by the way, a stress measured exactly in the proportionality limit. This is the equation 24.2, which should be pretty much memorized and which should be kept consolidately in mind, just to be reviewed in case of you having test for the tensile test, or even in case of you be examined by the tensile test. Hyperelastic resilience is an energy loss by the metal after the effective load, which is part of the, or even segment of the work done by load or by hyperelastic loading, which is in the form of the recoverable energy of any load, measured by the area under the curve, or the representation curve, or even under the graphical representation curve of stress strain diagram, or even for the load extension, the load elongation diagram, which is pretty much the bounded area by a line parallel to the curved line for the elastic region, as also for the parallel line to the vertical illustrated load axis, as clarified in the figure 13.2. And the resilience coefficient, or even the modulus for the resilience, will be the area of the graphical representation of the stress strain curve, or the graphical representation stress strain curve corresponding to the mentioned, or corresponding to the stipulated area of the load extension curve. As you can see right here for you, this strain is as usual is plotted to the horizontal axis of X, as well as the stress is pretty much vertically plotted to the Y-X, or the upward to the Y-axis, as you can see right for you, is collected upward, as well as the strain is also collected rightward, according to the two-dimensional plan of the stress strain curve representation. As you can see, the point of origination, as with the stress strain axis, both axes are intersected right at, which are pretty much orthogonal and perpendicular to each other. And the elastic line is generated right from to a certain limit called the upper limit, and this is the elastic resilience, and this is elastic resilience in the elastic region, as well as indicating by the triangle, or even indicated by this triangle of point 1, the hyperelastic resilience core to be, or even said to be, exactly the plastic elastic region. This is from the point B to point A. From point B to point A, this is the plastic, or the hyperelastic resilience, occurs exactly at the plastic elastic region. The visualization, as you can see right here before you, is pretty much of maximum essentiality here to be considered as for the appropriate, or even as for the optimal visualization for the resilience and the hyperelastic resilience of the stress strain curve behavior, denoting or even explaining this stress strain curve behavior. The figure 13.2 is actually visualized, or even visualizing the resilience in terms of the stress strain curve in case of hyperelastically loaded, or in case elastic loading, or in case of hyperelastic loading. The toughness. Toughness is the particularity of material, or even the property of material, or even the feature of materials express the ability to absorb energy by loading till fracture. And this particularity is pretty much ductility of materials and strength dependent. which is also resisting or even strengthening or even resisting the major effect or the major formations affected by the entire high or by entire enormous dynamic loads or the loads resulting from the impacts. The toughness is actually equal to the area of the load extension graphical representation diagram since the beginning or since the commencement of the loading till fracture. And the toughness moduli is actually already not the beginning of loading, but a certain at a certain point of loading till fracture, at a certain point other than the beginning here, at a certain point of loading till fracture. The modulus of toughness T is actually to be the strength or the resisting of impact to the volume of the testing spaceman, which is pretty much equal to the area of the graphical representation diagram of stresses and strain as illustrated in figure 14.2. More area or broader area you can get more strength of the metals will be gained, or more strength of the metal will be exhibited or even will be displayed for the dynamic loading, resulting in a more impact resistance. As you can see right from the figure 14.2 is the graphical representation for the stress strain curve, illustrate the method to determine or even to specify the modulus of toughness. The stress is vertically plotted, as well as the strain is horizontally plotted to the x-axis, and the stress is vertically plotted to the, or even plotted vertically plotted to the y-axis, vertical axis vertically. And this is the elastic range, or this is the toughness for the brittle material, as well as this toughness for the ductile material. As you can see, the toughness for the brittle material is even better than the toughness of the ductile material, just because the ductile material is actually failed right after a huge load recycles, or even right a huge load cycle to the materials, or even the brittle material is actually not failed until a certain material layer or until a certain load or a certain point of load is actually achieved. Then the material will continue to take course, even will continue to travel right through their course or their trajectory in the stress strain curve till a certain point called the point of the point of stopping, or even the point of the point of ultimate tensile strength in the brittle materials. Notation: any metals that have high resistance, this mean has a pretty much means or necessarily means that is actually possessing a higher toughness. For example, or if for size of the illustration, the figure of 14.2 for the high steel carbon has a high resistance but actually a corresponding toughness, the area of the curve, as compared to the moderate carbon steel, which has a very relatively high resistance but at the high toughness in the same time, as well as in the same instance, similarly represented by the area of the curve. Consequently, or even subsequently, the ductile materials has the higher toughness. This is illustrated precisely or illustrated accurately in the figure 15.2 for different examples of the steel sorts, or even for various examples of the steel sorts, illustrated in figure 14.2 for a variety examples of the steel sorts. As you can see right here, very good, is the representation for high steel carbon or high carbon steel, as you can see, or moderate carbon steel, with the comparison between the strength as well as the toughness rate, or the toughness value and the strength value at the same time. Comparison or corresponding comparison, or a comparison of correspondence, as you can see right here. Comparison for correspondence. يعني هنا مقارنة من أجل مقارنة مناظرة. أو correspondence comparison، يعني مقارنة مناظرة، يعني مقارنة بين المقاومة والمتانة المناظرة، أو المتانة والمقاومة المناظرة. As you can see, this is comparison between the strength and the corresponding toughness, or even the toughness and the corresponding resistance, or the corresponding strength. As you can see right in front of you, the high carbon steel is actually represented by the curve considered to be high carbon steel, or considered to be ductile materials, or even the moderate carbon steel is even more ductile, as well as the carbon steel is high resistance as well as more toughness it will get, or even more toughness the carbon steel, the more toughness the carbon steel will get, or even more toughness he will get. As you can see right right for you, this is the elastic limit, or this is the elastic line indicated from the stress origination, or from the point of origination at which the stress and strain, both axes, both perpendicular to each other, axes are intersected right at. As you can see, the line of elasticity is launching right, or originated right from point origin to a certain point called the point of elasticity, or point of the E, or the Young modulus, or the Young modular determination. As you can see right for you here, the upper yield point and the ultimate tensile strength will reach a limit here at the peak, or even at the top, plotted right in the stress strain curve, till reaching a fracture toughness, or even to reaching a fracture point at which the toughness will be final, or even at which the ductility will be finalized exactly and definitely at this point. So the high carbon steel here, as you can see here, the strain is horizontally plotted as the stress, and the stress is vertically plotted. The stress here is as follows: the vertically plotted, as well as the strain is horizontally plotted in the both diagrams, or in the both schemes, or even the both charts, or even in the both curves, as you can see right in front of you. So the high carbon steel with high resistance, or moderate resistance, and moderate toughness in the same time. For the moderate carbon steels, high carbon steel, high resistance is going to be like high resistance, and the comparison is actually here for the moderate carbon steel and the figure A. In the figure A, the comparison is mainly done for the moderate carbon steel, or mainly done for the high carbon steel as well as the moderate carbon steel in the toughness region, or even as a comparison between the strength and the corresponding toughness, or the toughness and the corresponding strength in the same time. And as you can see here, the dashed region, or the dashed, or even the shaded region, is actually pretty much indicating the toughness, or the area of the curve, or the area of the stress strain graphical representation curve. The following two subsequent figures, as you can see right here in front of you, is actually pretty much indicating the high carbon steel and the cast iron toughness, or the cast iron toughness shaded area, or the toughness area bounded, as well as the high carbon steel toughness area bounded. As you can see, the dashed area, or the shaded area, just like we stipulated before, or just like we formally indicate, as the way that the dashed region referred to is the toughness as compared to the corresponding strength. This is the higher strength and moderate toughness. The moderate carbon steel, as well as the GM indicated, as you can see right before you, and the stress and strain here indicating the cast iron. The cast iron, hadid al-zahar. The cast iron is a very brittle material, as well as very brittle substance, or very brittle spacemen to be used to conduct the microstructure, as well as to conduct the toughness of modulus, or the modulus of toughness here, the moduli of toughness, and indicating a moderate toughness, as you can see right here before you, as indicated in figure 15.2, the determination of the modulus of toughness for a variety, or even a variety features materials, or even variety features metals, such as the high carbon steel, more strength and toughness, and the moderate carbon steel is more moderate strength and with corresponding moderate toughness. As you can see, the cast iron is actually pretty much embrittlement, or even embrittle material, as well as via, or even as well as a moderate toughness, or corresponding, or conjugated with moderate toughness, with moderate corresponding toughness. Empirical results, or empirical outcome, or empirical representation by equations here for the toughness, as well as the toughness, the modulus of toughness. The toughness is called the area of the load extension curve, the area of the load extension curve, or the area of the load elongation curve, or the area of load elongation curve. The resulting in the finalization for the function, as you can see right in front of you, for the toughness in the equation 24.2, the toughness is equal 1 to 2 the yield load plus the ultimate load times the overall extension, or even the overall elongation, or the total elongation, or the complete elongation, the accomplished elongation. The modulus of necessity equal to the area of the stress strain curve, or the area of the load elongation, or the load extension curve via, or even v, or conjugated with the volume of the spaceman used. The equation 26.2 is the modulus of toughness equals to the finalized form, or even the final form of the equation of for modulus of toughness will be in the form of 1 to 2 the yield load plus the ultimate load times the overall extension, or times the total extension via the spaceman volume. Article 3.9.2, the high stresses. If any material in elastic region was repeated, or even was susceptible to a repeated cyclic loading, which is a loading for a several interval of time, or even for an ambient interval of time, and then it was loaded
afterwards and regain or even repeating the same operation or repeating the same procedure or task multiple times, here some of the energy of the entire energy will be lost by the material or even absorbed right by. If any material or any metal was stressed hyperelastically with a certain loading, then this loading was reloaded again over and over, so the stress strain graphical representation curve will contain most of the times of a cycle consists of two lines instead of as usual. If the loading is actually will reload again as illustrated or even as clarified in figure 16.2a, and this cycle will be denoted as the high stress cycle, and the area bounded within the cycle of the stress strain graphical representation curve is about to be an energy for any unit volume, for each unit volume lost as a result of a singularly valued cycle of the load and reload, and this lost energy or as a result for a cycle of load and reload. Which means that the area bounded of the cycle, or area bounded within the cycle here of the stress strain graphical representation curve is about to be an energy for any unit volume, or for every unit volume lost as a result of a cycle of loading and reloading. And this lost energy will be in the form of heat, as this aspect also coexist in and this aspect actually coexist by or even displayed or even exhibited by the non-metallic metals or non-metallic spacements such as elastomers, and illustrated in figure 16.2b. As you can see right here, the stress is loaded vertically as well as the strain is loaded horizontally, as well as these in figure B, the stress is loaded vertically as well as the strain loaded horizontally, just like we stipulated before. This is the high stress cycle of the loading. Repeated loading for a cycle for a certain interval of time for several minutes or even for several times will be resulting in the formation of the high stress cycle of the load extension diagram, or at the stress strain diagram. The load will be generated, or even the load elastic moduli. The load elastic moduli oblique line will be generated right from the point of origination at which the stress and strain both curves are, or the both lines are intersected right at until a certain limit, or called the point of yielding. As you can see right here, from the point of origination to a certain point called the point of yield. Then the entire behavior of this stress curve will be continues to travel right through to the future point of where the load is going to be like even as quiet as possible. If the world will be as calm as possible, then it will be reloaded again right where the arrows is actually going right through, or the arrows wise, or the arrows wise actually going or traveling right to the destination at which the loading is actually will be count right at, or even the loading will be even will be settled right at, and we will be reloaded again till a certain limit called the limit of the elasticity, or even the upper limit, as you can see, the upper limit of yielding. So hence there are 3 points of yielding, as you can see right in front of you here in the plotted stress strain diagram right in front of you. You have the point of yield, the first point, the yielding point, as you can see right in front of you, as well as the second yielding point, as well as the third yielding point, as a result for load settlation right at as a result for the cyclic action, as you can see right here in front of you. This is the figure 16.2, the graphical representation for the stress strain diagram. It illustrates the high stress cycle for the soft steel or the wrought steel, and for elastomer A, as well as the wrought steel B. Now we're just going to have to visualize the article 10.2, the types of structures. The types of structure are subdivided or even divided for the resulting, or the types of structure resulting for the metals, of the resultant metals from the tensile test according to the following, or according to this as follows. First, or according to the following. First, the formology, or even the shape, or even the form. The fracture could be identical, such as the glass fraction, or even such as the glass fracture, or even the conic fracture, or the flat fracture, or the uniform or truncated fracture. And the fracture may be heteromorphic, or even the fracture could be, or even may be heteromorphic. يعني قد تكون الكسور غير متماثلة, heteromorphic. 2. The condition of the surface condition. So describe the surface either by the smooth, fine, or the fine surface, or by the macro or the micromolecules, or micromolecules, or the macromolecules, or the fibers, or the crystallized, or even vitreous. The fibrous surface, or the fibrous condition of the surface, or the crystallized condition of the surface, or the vitreous condition of the surface. Vitreous هي الزجاجي، الحالة الزجاجية للسطح. 3. The colors. The specs of the fractured color is the brightness, or the bright color, or even the dark color. the bright color or even the dark color, as you can see right here in front of you. The bright color or even the very heavy color, the heavy or the bright color, as you can see, the bright or the heavy color. And for the source metals or the source of the variety of metals, the fracture will be as follows. يعني بالنسبة لأنواع المعادن المختلفة, and for the size or with respect to the various sorts or even for the various types of metals, so the fracture will be as follows. Ductile materials or ductile metals. When a sample of the road will be susceptible or even will be exposed, which is very much ductile, so the elongation or extension will increase gradually with or via the loading to reaching the elastic limits as well as the stress of yielding, then the plasticity will be triggered. As well as the loading will be increased gradually to releasing a highest tensile stress or even a maximum load, which is the ultimate tensile stress, then the nicking will be triggered as well. So a major deformation or a major formation for this basement will be taking place just before the fracture in the form of glass fracture or in the form of connect fracture. Well, the entire surface will be coarse in this case in mid of the transversal truncation and very fine smooth at the ledges. يعني من الأسنان عند الحروف يعني عند الليجز يعني الحروف يعني الحافات. 2. Semi-ductile materials, as you can see right for you. The stress strain graphical representation curve for the semi-ductile materials has the same typical form for the ductile materials, but only with the yield region. As well as the load is more effective, as well as the elongation is pretty much identical to its corresponding of the ductile metals. The fracture will be in the form of glass fracture or the connect fracture, but with nicking as much as or even as compared to the nicking of the ductile materials or of the ductile metals. 3. Brittle materials. The stress strain curve is featurized for the brittle materials since the beginning by in form of an oblique line or even in the form of inclined line, and that to be aligned, as you can see here. The metals will experiencing a very small deformations as compared to the foreign materials, as well as there will be nicking, and the fracture will actually takes place when the loading is reaching the maximum optimal limit. Here, the fracture shape or the fracture form or the fracture formology will be in the form of the vertical plan to the orientation of the tensile force, whether it was or even the plan, whether it was the plan, or even tensile force is actually whether the tensile force was actually pretty much a flat or even protrusive. Protrusive يعني محبب or grainy, flat or grainy. So the entire surface will be either flat or grainy. The entire surface at which it is very much perpendicular to the orientation of tensile force will be either flat or grainy. And the forms of the fractures actually will be illustrated in the figure 17.2 and as well as the figure 18.2. As you can see right in front of you, this is the protrusive and the protrusive form of fracture, as was this the iliased form of fracture. The iliased يعني المتعرج, the iliased form of fracture, as well as this is the ductile material form of fracture, which is said to be very much homomorphic. This is the homomorphic type of a fracture, or the homomorphic image or the form of fracture, as you can see right in front of you. Homomorphic يعني متساوي الشكل، أو homomorphic يعني متساوي، أو homomorphic يعني منتظم الشكل. Homomorphic منتظم الشكل. The figure 17.2 is the types of fracture or the forms of fractures of the tensile test for ductile materials, semi-ductile materials, illustrated in figure ABG. Figure 18.2 illustrating the figure, or illustrating with the fracture form for the glass or the truncation, or the connect truncation, which appears at the ductile fracture or the semi-ductile fracture. This is the typical fracture form. Article 11.2, the affecting agent for the tensile features of metals. Article 1.11.2, the testing variables. Speed of loading while testing. More speed of loading while testing the ductile materials as the semi-ductile materials, increasing the strength, the tensile stress, as well as the yield stress and the ductility of metals, as well as the brittle materials will not be very much affected would be very much affected by the speed, pretty much substantially or even extremely affected by the speed. The brittle materials, as we. so too the heat while testing, or the heat of the testing. If the temperature goes up, or even the temperature go up, so the tensile strength will be, as you can see, as well as the ductility will be as illustrated, or even will be increased as illustrated in figure 19.2 for steel. This is considered right here, the figure 19.2, the effective temperature to the stress strain curve of steel of tensile test. This is the effective temperature is actually affecting the same materials, but resulting in differentiated behaviors for the stress strain trajectory. As you can see from here, it results in pretty much differentiated behaviors for the stress strain, or even differentiated behaviors not for the stress strain curve only, or not for the stress curve in whole, or in total, not for the stress strain curve, but only for the curve here, resulting in differentiated behaviors for the curve only, but not the stress strain. As you can see, for the differentiated behavior, as you can see, from the 200, as you can see, to 25 degrees centigrade. This is the strain is actually plotted to the horizontal, as well as the strains are plotted vertically to the y-axis, 200, 400, 600, as you can see right for you, 0.2, 0.3, 0.5. The figure 19.2, just like we stipulated for the effective temperature to the stress strain curve of steel of tensile test, that actually tensilely tested. The stress is measured by megapascal as well as the strain. 3. The cold working. يعني تشغيل بالبارد. The cold working is loading or even stressing the materials hyperelastically. They're reloaded again for several times in a cyclic action, resulting in improvement in the yielding stress as well as the proportionality limit, and as well as the tensile strength and resilience and the hardness of metal, but ductility and toughness, but corresponding, or even better for us to say, but in ductility and toughness. The modulus of elasticity, or even the elasticity moduli, or Young moduli, is mostly remain constant, as illustrated in figure 20.2. As indicated here, the stress and this strain in the same time here is actually the stress, or this strain is 0.05 in range. As you can see right for here, differentiated behavior for the curve is actually indicated, or even is actually stipulated, as you can see in the gridded scheme, gridded diagram. As you can see right here before you, the stress is vertically plotted and the strain is horizontally plotted, indicating the cold working rate affecting the curve in a different, or even in affecting the not affecting the curve, but actually affecting the behavior of material for the same material, the behavior on the spacemen acquired or even required to be tested, required to be examined by using the tensile test. As you can see here, this is the elastic limit line, oblique line, as indicated here, extends from the point of origination at which the stress strain axes are intersected right at till the point of 200, as you can see right in front of you. So the differentiated behaviors will be indicated, or will be emerged right from the point of the upper yielding right into a certain limit called the limit of a fracture, at which the material will be fractured right at. This is the cold working with this strain, the cold working rate with this strain, with the increasing of the strain, or even with the oscillation of the strain, will be pretty much affected to reach a certain level certain level of values, where the values of the curve will be totally be gauged accordingly with the standardized results, or the standardized entire results coming from, or even extract from the standardized global specs. The figure 20.2, the effective cold working, the stress strain curve for a steel alloy of tensile test, or for a steel alloy tensile tested. The article 11.2, the variables of the testing specimens. First, the formology, or even the form, or the factor, or the form, or the shape of testing specimen. The shape of testing specimens is extremely effective, the tensile, as you can see, and obviously as well. So for size, if you take different shapes, specimens as illustrated, or even as clarified in the figure 21.2, and tensile tested till fracture, so the stress strain graphical representation curve for each specimen will be pretty much different than the will be pretty much different other other than the four others. Subsequently, the entire specs will be differentiated. As you can see here, for different placements, see the length will be constant, or the length will longitudinally increase, as well as the D will laterally increase. In case if you're having a compression test exerts, or in case of having, or even in case if you're imposing an compression test to the testing spaceman, as you can see right in front of you. The testing spaceman is actually prior to test will be in the form, or even will be in the length to diameter ratio of the valued, or even the valued stated, or even the valued written as follows, or visualized as follows, right here before you. And during the testing, LD to be positive, and LD will be 2, and as well as the LD will be 3 at a certain point of the testing procedure. As you can see right here in front of you, the point ESB is actually indicating the testing spaceman for a variety, or even testing spaceman for a variety of samples, such as the tactile samples are the trajectory of the tactile samples of commencing the point of yielding, as you can see right here, from the upper yield point right till a same ultimate tensile strength, where the trajectory, the entire trajectory, or even the orientation or the direction of the curve for the entire, all three ABC specimens used for testing, for conducting the test, is actually pretty much differs. So the specimen B will be in this orientation, as well as the specimen A will be in this orientation, as well as the B will be in this trajectory, as well as the trajectory of specimen C will be in this, until reaching a certain amount of values for the specimen B, D. So it will be in case of 3 o'clock orientation, and the E is 12 o'clock upward. This differentiation, as you can see right in front of you, it comes as a result for the testing spaceman formology effect. The figure 21.2 is the effect of the testing spaceman shape in tensile test. Two, the carbon content of the steel. The carbon content of steel is actually highlighted affecting agents. The steel, as you can see right here, highlighted affecting agents in the alloys. So any increase in carbon content of the steel will result in as follows. Will result in the following: increase in the proportionality limit stress P or sigma P, the yield stress yield or sigma Y, and the tensile strength or ultimate tensile strength UTS, as well as the resilience UR. As you can see right there, for the ductility and toughness, as illustrated in figure 22.2, as the figure clarifies or even disambiguates that the tendency of the stress strain curve in the elastic region, the Young modulus frontiers, has only singularly valued for all various types, or even for all various sorts of steels of carbon content, or for the entire carbon content variety sorts of steels, as well as the heat treatments, which means, or e.g., that the stiffness of the entire steel source can be considered, or it can be considered unitarily valued approximately to 200 gigapascal. Unitarily valued يعني مقيمة بقيمة أحادية، أو اعتبارها قيمة واحدة، قيمة مفردة يعني. And as you can see right here for you, this is the stress is actually vertically plotted, as you can see right here, measured by the gigapascal, or measured by gigapascal. Of course, it's gigapascal, as well as the strain is vertically or horizontally. It's horizontally plotted, as you can see right here, for a variety of metals, or even as you can see right here, the heat treatment for the chrome tungsten alloys, as well as heat treatment for the nickel alloys, Monel, and the heat treatment for the carbon 0.52%, as you can see, as well as the elastic modelling for each, for the entire metals, for the entire solid alloys represented, or even presenced here in the gridded diagram of this stress strain curve, is equaling, or even equals to 200 gigapascal, as you can see right here in front of you. This is the main curve of the stress strain diagrams for a variety of alloy of steel alloys that actually pretty much differentiated in carbon content, or pretty much is actually containing a carbon content differentiately. carbon content differentiately of the steel alloys present in the gridded scheme, as you can see right in front of you, the gridded scheme, or even the gridded diagram of stress strain curve. The differentiation exactly in the stress strain curve, as you can see, or in the curve, not in the stress strain, the differentiating of the behavior. Basically, the behavior is actually here is differentiated very much. The differentiation of the behavior is actually due to يعني يعزى إلى الاختلاف في التصرف. The differentiation of the behavior is, or differentiation of the behavior, as you can see, for each alloys that actually presents here, as you can see, or the actually here in the diagram is due to the pretty much due to the basic reason, or the fundamental reason, which is mainly considered as the carbon content. This is the carbon 0.32, as this is carbon 0.52, and this is the carbon 0.32, and the carbon 0. As you can see right here in front of you, presents in the stress strain plotted diagram. The stress is in megapascal, plotted exactly commenced at the point of origin, 0 till 1000, till the 1000 gigapascal, or the 1000 megapascal, which considered to be 1 gigapascal, or even 10,000 gigapascal considered to be 10. 1000 megapascal considered to be 10 gigapascal. As you can see right from here, the 0, 0.002, 0.08, and 0.0 as illustrated, as digitalized, or even as plotted horizontally right here before you. The figure 22.2 illustrated, as you can see right here before you, is clarifying the effective carbon content in tensile, or of tensile test. حاجة ستريس ترين والله. Heat treatments. As a procedure at which the metals is heated, especially the steels, to a very certain temperatures for a very specific limited interval of times, and will be cooled either at different cooler rates, at different cooler rates, will be cooled in different cooler rates, or will be cooled at different cooler rates, such as rapid cooling, such as quenching, or such as rapid cooling, quenching, or even slow cooling, to alter the metals, as well as to gain a very good property, or to gain very fine features. The material or the heat treatments is actually pretty much indicate the utilizations of special heating kilns, as well as water basins and cooling oils, and the highlighted heat treatments to be introduced to the alloys are as follows: tempering, or even quenching, التقسية. The steel will be heated to an elevated temperature, then will be cooled suddenly in the cold water, and this treatment increase the tensile strength substantially, but with corresponding ductility, as you can see right here for you. The annealing, التخمير. The annealing, the steel will be heated to elevated temperature, then will be kept at this temperature for a variety, or even for a while, and then will be slowly cooled within the kiln, and this treatment basically improves, or even basically enhances the tensile strength, as well as the yield stress and the ductility and the toughness. The tempering, التطبيع. The steel will be heated to a moderate temperatures, then will be slowly cooled, and this treatment improves substantially the tensile strength, as well as the ductility and toughness of the metals, increasing the brittlement. The metals are used in industry after proceeding the heat treatment right or even after they are or even after they are thermally treated. And the table 1.2 is illustrate the mechanical features of tensile for metals. As you can see right in front of you, the specialization of protection mechanics, the metal is in the condition of the metals while heat treated, while it's heat treated, or the condition of the metal while the metal is actually in the kiln, or while the metal is actually the metal is treated by the kiln, or even not treated by the kiln, in the kiln. And the yield stress is actually given by the prefix of yield stress, or the sigma conjugated with the letter y, indicating that the stress is actually yield stress of the 0.02% sigma proof of the 0.02% or the ratio of 0.2, as you can see, 0.02 ratio of sigma proof measured by, or even scaled by the kilogram millimeter squared, as well as the tensile strength, the sigma b, and the measured, or even also scaled or unitized by the kilogram millimeter squares, as well as the modulus of elasticity, or even the elasticity, or the Young moduli, times the entire value of the elastic moduli is actually times, or even productly multiplied by the 10 cubic or the 10 to the power 3, also utilized or even measured by the kilogram millimeter squared, and the ductility EI, percentage of ductility, or even the ratio rather than percentage, 100%, L naught by the initial gauge length, initial standardized gauge length of 50 millimeter. As you can see right in front of you, we have a wrought steel or even soft steel, annealed. The condition is annealed. The yield stress is for the wrought steel is 30 kilogram millimeter squared, or even 30 by 30 measured according to the standardized 0.02 proof stress ratio, or 0.02 proof stress strain. Proof stress value. 40 here for the tensile strength. As you can see, right, for the sigma B is measured 40 kilogram millimeter squared, 21 modulus of elasticity by the 10 cubic, or by the 10 to the power 3, as well as the 37. The ductility is indicating 37 for the wrought annealed steel, or the annealed wrought steel, as you can see right in front of you, according to the standardized gauged length. The moderate carbon steel is actually annealed. The conditionized is actually annealed. The condition of the moderate carbon steel, as you can see, is annealed, and the 35, this is the yield stress according to the 0.02 ratio of the proof stress, or the ratio of or the value of proof stress, as you can see right in front of you. The tensile stress is indicating 52, as well as the modulus of elasticity indicating 21 times 10 to the power 3, or times 10 cubic kilogram millimeter squared, and the ductility is actually indicating 30 according to the standardized initial gauge length of 50 millimeter, L naught, as you can see right before you. يعني أمامكم. The regular steel is annealed, 35 as you can see right for you for the yield stress 0.02, and 55 for the tensile stress or strength. As you can see for the elastic moduli is 20 by 10 cubic, as you can see right for you, kilogram millimeter squared, or megapascal, or even kilopascal, kilopascal by 10 to the power cubic, or if it's going to be like in megapascal, 20 by the standardized initial gauge length of 50. Moderate carbon steel is hot rolled. Moderate carbon steel hot rolled, يعني مدلفن بالساخن. 51 for the yield stress 0.02%, as well as the 83 for the tensile strength, as well as 20 for the 20 by or times, يعني في by أو times يعني في مضروب في by or times as you can see right for you by the 10 cubic for modulus of elasticity, and 34 for the ductility of 50 millimeter. The high resistance steels is oil quenched يعني مقصى في الزيت. 97 for the yield stress of 0.02 proof stress, and the tensile strength is indicating 152 value of kilogram millimeter squares, as well as a 20 times 10 cubic for the modulus of elasticity, or Young modulus, as well as a 12 here for ductility with respect to the initial gauged standardized length. The malleable iron, or even the mild malleable iron, as you can see, is hot rolled يعني مدلفن في الساخن. مدلفن ساخن. Yield stress is actually 0.02 for the proof stress is 21 indication, gives 21 indication, and 35 for the tensile strength of kilogram millimeter square, and 19 by or times 10 cubic for the elastic moduli, as well as 30, as you can see right in front of here, as well as 30 for the ductility ratio. Cast iron casted مصبوب يعني. As you can see right for the 1811 0.50, 1811 by the 10 power by the 10 to the power 3, or the 10 by 11 by 10 or times 10 cubic, as you can see for the 0.15 for the ductility. Pure aluminum, or even intrinsic aluminum, hot or cold rolled مدلفن بارد. 15 for the yield stress, and 17 for the tensile stress, and 7 for the modulus of elasticity, and 16 exactly for the ductility ratio. Or 16 is actually indicating the ductility ratio. 4 for the hot rolled, or even cold rolled iron. Cold rolled iron, as you can see right in front here. Molybdenum annealed, MB. The yield stress is 57, as well as 66, and for the tensile strength is best ever, maximum it can be, as well as the 33 by or times the 10 to the power cubic, 10 to the power 3, as you can see right in front of here, 35 for the ductility. Pure aluminum, or pure copper. Pure copper is actually a cold roll. We have pure copper, or even we have intrinsic copper, as you can see, cold rolled, as well a cold rolling. It's actually pure copper is actually conducting the cold rolling, and the pure copper, or even intrinsic copper, as you can see right in front of you, conducting the annealing. 33, 34, 11 times 10 to the power 3 or 11 times 10 cubic and 5 for the ductility. 11 times 10 cubic, which is we stipulated before, is for the modulus of elasticity or the elastic moduli. The copper or the pure copper, as you can see, or the intrinsic copper is actually conducting the annealing. 69 and 22. Tensile stress. 69 is yielding stress for 0.02 of a proof stress, and 11 times 10 to the power 3 or 10 to cubic is the is the elastic modulus, and 60 is the great ductility ratio, as you can see right in front of you here. Phosphorus bronze alloy or phosphorus bronze volume is actually annealed 15, 34, 9 times the power to 10 to the power cubic, or 10 cubic 10 to the power 3, 50 for the ductility. This is for bronze. 15 is actually pretty much for the 0.02 tensile or yield stress, proof stress. 34 for the pretty much 34 indicating the tensile strength of sigma p. Nickel copper alloy conducted for any, or even conducting the annealing, يعني التخمير. 14 for the yield stress of 0.02 proof stress, and 38 for the tensile strength, and 50 for the elastic moduli. 15 for the elastic moduli, as you can see right in front of you. 15 is actually indicating 15 times 10 to the power cubic, or 10 to the power 3 or 10 cubic, and 28 for the ductility ratio. Pure silver or intrinsic silver is conducting the annealing. 8, 13, 76 times 10 to the power cubic, or 10 to the power 3, as well as the 45 for the ductility ratio. The intrinsic titanium is is conducting the annealing. 33, 24, 11, 24 for the yield or the tensile strength, and 33 for the tensile, for the yielding stress of 0.02 proof stress, and 11 times 10 to the power cubic, as well as the 30 here for the ductility ratio, or the 30 is actually ductility proportionalized. The pure nickel or even intrinsic nickel, as you can see, conducting the annealing. 21 for the yielding stress of 0.0 proof stress, and 14 for the ultimate tensile strength, indicated as sigma p, and 21 times 10 cubic for the elastic moduli, as well as the 40 here indicating the great or the best it can be ductility ratio. This is the table 1.2, the mechanical features of the tensile test of metals. بسم الله الرحمن الرحيم. Chapter 2. Solved examples. يعني وحدة ثانية مسائل محلولة. Example 1.2. Tensile test was conducted to specimens with a larger length of 50 mm and elongated to the 51.7 mm. Calculate the following. 1. Calculate the engineering nominal strain value and the true strain value. يعني قيمة الانفعال الهندسي الاسمي وقيمة الانفعال الحقيقي. أول قيمة الانفعال the actual strain value. Done. The solution will be as follows. يعني الحل كالتالي. أولا, from the relevancy or from the relationship 3.2, the engineering nominal strain E is going to be as follows. For the L naught equal to 50.0 millimeter and the LF to 51.7 millimeter. E equal delta L, as you can see, LF illustrated in the following equations, equals to yields the 51.7 minus 50 is going to be like in the form of equals to 0.03 equals to 3.4. As you can see right in front of you, this is the rate of strain. This is the great ratio of strains. Of course, it's going to be like horizontally plotted to the x-axis. 2. Thermal relevancy 5.2, or thermal relationship 5.2, the true strain, or even the actual strain epsilon, indicated or even denoted by epsilon, the Latin prefix indicating the true strain for the metals and for the metals in tensile test, or even for the metals of tensile test. Epsilon or tensile test at epsilon equal to ln LF and equals to ln 51.7, as you can see right in front of you, equals to 0.033 equals to 3.3, as you can see right in front of you. Or by evaluating in the equation 8.2 directly, epsilon equal to ln E plus 1. This equation, this great brightness equation, or the equation of exquisity, is actually pretty much considered the equation of relevancy or equation of correlation between the engineering strain, nominal strain, which is indicated by the E letter, as you can see right here in front of you, as well as the epsilon, the true strain or the actual strain, equals to ln 0.03 plus 1, 0.033 equals to 3.3, as you can see right in front of you. The example 2.2. tensile test was conducted, or the tensile test was proceeded to as a tensile testing specimens with a gauge length equal to L naught equal to 100 millimeters with rounded cross-sectional area diameterized as D naught equal to 20 millimeter. يعني diameterized يعني قطرها diameterized diameter قطر diameter قطر diameterized or diameterized as D naught equal to 20 millimeter. The observations of the load were scaled or even were gauged by ton, as well as the corresponding elongation was gauged by the millimeter as follows. The load is actually indicated or even scaled or even utilized or even measured by the ton, 3.75, 7.5, 7.5, and 8.5, 11, 0.0, 12, 12.5, 11.5, and as you can see right in front of you here, hash 11, hash 10, hash 11, hash 10. The elongation is actually measured by the millimeter, 0.0, 0.1, 12, 1.12, 24, 25, 29, 32. The table is actually very much scheduled or even grouped according to the following standardized or even to the global standardized specs of tensile test. The required is as follows. The required is as follows. يعني المطلوب هو كالتالي. المطلوب محدد الآن. Plot load and extension curve, then assigns the following. يعني ارسم منحني الحمل والاستطالة ثم عين ما يلي. Yield stress, tensile strength, and the elongation ratio, as well as the modulus of elasticity, modulus of resilience, and modulus of toughness. The solution will be as follows. Or the solution in this case will be accomplished as follows. This is the graphical representations of the sketch of the load and extension diagram. As you can see right in front of you, the load extension diagram for the table grouped as follows, or even scheduled as O2, 8 to educate for 10, 12, 14 and counting, or the 10, 12 and counting till 14. The load is actually measured by the ton, as well as the strain or the extension measured by the millimeter, as you can see right in front of you here. The linear elastic moduli, or the linear elastic optic curve, is actually extending or generated from the point of origin at which the stress and or at which the load and extension are intersected right at till it reaches a very 7.9 or 7.8 value of the upper unit limit, or the value which consists the peak of the elastic limit. Consider the peak of elastic limit exactly at this point, 7.8, and the upper yield point then will be nicking. There will be an area of nicking until reaching an ultimate tensile stress of the 12.4. The ultimate tensile stress is 12.3, as you can see right in front of you here, until the fracture point of 9.9. This is the fracture point, as you can see right in front of you, all indicated in the following gridded scheme, or even in the following gridded load elongation diagram. The area is rounded. The area is with rounded cross-sectional area. So the original cross-sectional area A naught will be as follows: A naught equal to pi times d squared equals to pi times 20 squared equal to 300 millimeters squared. This is the area of the rounded testing spaceman. From the relevancy, or from the relationship 1.2, the yield stress sigma y equals to the yield stress equal to FA naught, as you can see right in front of here, equals to 7500 equal to 23.95 kilogram millimeters squared. B, from the relevancy, or from the relationship 19.2, the ultimate tensile strength, or the ultimate tensile stress denoted by the sigma UTS, can be measured or even can be computed as follows. The sigma UTS equal to F max equals to 12 12,500 equal to 39.90 kilogram millimeter squared. Kilogram millimeter squared is actually indicating kilopascal. يعني كيلوغرام مليمتر تربيع هي كيلو باسكال نفسها. Elongation ratio is as follows. Computed is 32 times 100 equal to 32, as you can see right in front of you. From the relationship 50.2, the modulus of elasticity, or the Young moduli, is in elastic region, or in the elastic limit, equals to stress strain. So the E equals to as follows: sigma P equals to 3750 or 3750 equals to 11.94 kilogram millimeter squared. EP equal to 0.0 equal to the value, or even valued. The EP will be valued as follows. EP will be valued as follows. يعني EP سيكون مقمم، أو سيكون ذات قيمة كالتي أمامكم، القيمة العليا أو القيمة القصوى التي أمامكم، as the maximum or the maximal value right before you. E equals to 11.9 T, and equals to 19,900 kilogram millimeter squared. It was going to be like 19 megapascal, approximately, or 19 megapascal, estimatedly to be 19 megapascal. From the relationship, from the relevancy 23.2, the resilience of, or the modulus of resilience UR is going to be computed from the following equation, equals to 1 to 2 times sigma P times EP. Sigma P is the stress at the proportion, or the stress in the proportional limit, proportional, times the EP, the strain in the proportional limit. Sigma P is the proportional limit, as well as the E sigma, or the EP is the corresponding strain for the proportional limit. So, or consequently, UR is going to be like equals to 1 to 2 times sigma P times EP equals 1 to 2 times 7500 times 0.12 equals to 0.0, as you can see right in front of you, valued as follows: kilogram millimeter squared, millimeter cubic equal to 143 times 10 joule. Since the heat, or since the resilience is actually expressing the heat emitted or even absorbed by the system, absorbed by the entire spaceman, so it will be measured by the joule. Joule is then energy unit. So the energy will be utilized by the joule. From the relationship 26.2 is actually best. It can be the modulus of toughness T equals to 1 to have yield load plus the ultimate load times, or even by the overall extension, or even the total extension or the total elongations via the size or the volume of the spaceman used, and will be computed as follows. Good. T equals 1 to have times 7500 plus 12,500 times 32 equal to 10.1911, or 19,000, or 1,911 kilogram millimeter cubic equal to the following, as you can see right in front of you, 101, or 101,911 times 10 joule millimeter squared. Example 3.2. Tensile test was proceeded to an aluminium testing specimens with a diameter as 1 centimeter or diameter as 0.9 centimeters with a gauge length of 5 centimeters, and the observations of load were measured by kilograms, and the corresponding elongation was measured with the millimeter, as well as the while testing detection comes as follows. يعني كما رصدت أثناء الاختبار كما يلي. Got load in kilogram, as actually load is actually kilogram, 200, 0, 200, as you can see, 200, 400, 600, 8, as you can see right in front of here, till 1100 and 1150, or 1150, or 1150, or 1150. The elongation is as follows: 0.00, 0.000, 0.018, 0.35, or 0.05, and 0.072, 0.083, 0.105, or 0.150, and 0.270. Draw or even plot the curve for the loading extension or the load and elongation, then assign the follows: 0.2% or even 0.2 proof stress, the modulus of resilience, or the modulus of elasticity and modulus of resilience. The solution will be in the following form, or the solution will be formalized as follows. This diagram is actually for a very ductile material such as the wrought steel, or even very ductile material such as the, other than the wrought steel here, the ductile material such as the aluminium. Here the aluminium is actually indicating the following stress strain curve, as well as the proof curve generated from the 0.09 point plotted horizontally axis, or the horizontally axial strain, as you can see right in front of you, generated right from to intersect with the stress strain curve, as you can see right in front of you. This is the optimal, and this is the optimum plot for stress strain curve. Then we can only map the point of the proof stress to the vertical stress, or the vertical load, vertical axis of the load at which the load is actually plotted right at, to extract the proof stress or the proof load. Then, hence the proof stress, or then here comes the proof stress right after, or right as a result for. As you can see, for the elongation is plotted horizontally, as you can see for right in front of you, and this is the line. This is the line for elastic limit, indicating the limits, or even indicating the frontiers of Young modulus. Permanent elongation at the L stress here will be considered, will be taken as the proof stress, which is, that's the L proof, as you can see right for here, equals to, or even L proof, L proof equals to 0.2 times L naught equals to 0.2 100 times 50 equals to 0. As you can see right, 0.09 millimeter of the from the curve of load extension, or even of detecting or regarding the loading station curve, we can only find the proof load as follows. The proof load is actually equals to 1130 or 1130 kilogram. So the proof stress will be as follows. The original cross-sectional area A naught, since the aluminum specimen is actually in the following form, or in the following profile, or in the following form. So the area of the specimen will be as follows. Since the axial area susceptible to the axial loading is going to be like round, or even it's going to be like as you can see in the form, A naught equals to by times 10 to the power 2, or by times 10 square equals to 78.5 millimeters squared. So this sigma proof entirely will be computed as follows: equal to F proof equals to 11, or even equals to 1130 equals to the following. This is the proof load. This is the maximum or the optimal value for the proof load extracted from the gridded scheme, or extracted from the aluminum stress strain graphical representation curve by mapping the intersecting point between the proof line and the point of intersection. By mapping the point of intersection between the proof line or the proof line with the intersection, or intersected with the stress strain curve, to be mapped to the following horizontal, or to be mapped to the corresponding vertical axis of load. B, from the relationship 15.2, the modulus of elasticity in the elastic region is going to be like in the following form, or is going to be computed by the following equation. To if A, as you can see, by times L naught, as you can, equals to 200 times 50 equals to 77 or 7,077 kilogram millimeter squared. This is the elastic moduli. Unit 2, or even chapter 2, theoretical trainings. From the exercise, or the theoretical exercises. From the exercise 1.2 to exercise 8.2, select the right answer, or the correct answer out of the suggested 4 answers, or the suggested 3 answers only. The exercise 1.2, in the stress strain curve, or sigma E tensile test curve, and exactly at the point of yielding, the plasticity, or the elasticity, or the nick, or the fracture will be commenced. State the following correct answer. Exercise 2.2, in the stress strain curve, sigma E tensile stress curve, tensile test curve for ductile materials, the begins right from the point elastic limit, or the proportionality limit, or the maximum tensile strength, or ultimate tensile strength, and or from the yield stress. The exercise 3.2, the Young modulus, or the elastic moduli, is the moduli that permits to calculate and knowing the range of the plasticity of the material, or the elasticity of material, or the strength of material, or the acidity of the material. Exercise 4.2, Hooke's law will be applied in the tensile test, commencing the stress till elastic limit, or the yield stress, or the proportionality limit, or the UTS, the ultimate tensile stress, as stipulated before, or as stipulated previously. Good. The exercise 5.2 is the proportionality limit, or if the proportionality limit sigma stress and the corresponding strain E, so the Young modulus will be equal to stress plus strain and stress, as you can see right in front of you. The exercise 6.2, in the stress strain curve, the AX, or the sigma, or the axial stress strain curve of sigma E tensile test curve, the resilience coefficient, or the resilience modulus, will be calculated. The resilience modulus magnitude will be computed by A, the area of the stress strain graphical representation curve bound between 0 and the elastic limit stress, or the area of the stress strain graphical representation curve bound between 0 and fracture point, or the stress, the ultimate tensile strength value times the strength value at ultimate resistance or even or at ultimate or in ultimate resistance, as you can see right for you here, or the elastic limit stress value and the elastic limit strain value in the same instant. Exercise 7.2. In the stress strain curve, the sigma E tensile test curve is actually required to calculate the magnitude of the toughness criteria, or the toughness moduli of the material by the area of the stress strain curve bounded between 0 and elastic limit stress, as well as B, the strain of the stress strain graphical representation curves bounded between 0 and the fracture point, and the value of the ultimate tensile stress times the ultimate tensile strain value, and the elastic limit strain value via the elastic limit strain value. Good. The exercise 8.2, more elastic materials, we can get more multiplications of modulus of elasticity, or sustainability of modulus of elasticity, or more plastic material, or even increasing materials, or even increasing spaceman plasticity. بسم الله الرحمن الرحيم. As you can see right from the practice 9.2, tensile test was conducted to a spaceman of horizontal steel, or the spaceman of iron, as well as diameterized as 5 centimeters, and the gauge plate was 25 centimeters, and the load measured by the 10, as well as the corresponding extension or the elongation measured by the millimeter, as they were detected while testing, as follows: the load and elongation by millimeter, and the load by ton: 2.500, or even 2.500, or 5,000, 75,000, 10,000, 11,250, or 12,500, 13,500, or 13,750. Or the elongation is as follows, as you can see right in front of you, tabulated in the following digitalized values. Draw or plot the load extension curve, and then assign the following: 0.2 proof stress, modulus of elasticity, modulus of resilience, and modulus of toughness. تم بحمد الله.